All right. But as far as labs go, you still have an opportunity tomorrow night at the observatory. So beginning about 8 o'clock, they'll be there to show you the nighttime skies. So here is an active sun. Actually, that 11-year cycle, it ramps up for lots of sunspots and then not many sunspots, and lots of sunspots and not many sunspots. So about every 5 years, it's max and then it's min, it's max and it's min, kind of. So this is what, and when it's max, we call it active. So this is like an active sun. Okay, so I think that the video did a good job of saying if the energy coming from the sun was just regular, like burning stuff, okay, our sun would only last for 10,000 years. And you already heard him kind of throw out we've talked about the 4.6 billion years already. So that's about how long ago our sun turned on. And we've talked in here about you can take if it's spread out and it becomes smaller and smaller and smaller, you are converting potential energy, gravitational potential energy, into kinetic energy. And that's not it, because that would get us 25 million years. But this whole idea of nuclear fusion, just like the video talked about, that's what's going on in our sun. And I like how this unit of material is, because we're going to talk about our sun, and then we're going to go right into other stars. So it's kind of cool. Okay, so the thing about the sun and other stars is only in their centers are the conditions just ripe for nuclear fusion. And we kind of saw an animation with nuclear fusion. Basically, you need very hot temperatures and high pressures. All right, so about 4.5 billion years is about how long our sun's been cranking away. And we heard in the video this kind of 5 billion years in the future. That's about how long it's going to be what we call a main sequence star. We'll talk about what a main sequence star is. And it's not going to blow up. Basically, in that amount of time, 5 billion years or so, it's going to swell to become a red giant. That's just it. And I couldn't remember, but the video said what it's going to kind of go between Earth and Mars, orbits. So, but right now, it is in what we call gravitational equilibrium. I'm not sure the video really talked much about gravitational equilibrium. But gravity, okay, there's the gravitation is the gravity part of it. So basically we have, and here they are green arrows. Can you see the green arrows kind of pointing in towards the center of the sun? That's gravity. The red arrows basically are the sun's energy pushing outwards, kind of like we saw that the photon working its way out. That's energy from the sun working its way out. And so that's kind of, think of that as those red kind of things. And so they're basically equal. So that means the sun is not swelling, nor is the sun contracting. Now, I have a slide coming up that shows you it's doing just a little bit of this, but not much. It's not swelling like this out to the orbit of Earth, So it's kind of in between. So gravitational equilibrium. Anytime you see the word equilibrium, think equal. So something's equal. And in this case, the equal is the forces of gravity and basically the outward force of that the sun is exerting as it has energy in its core. Okay. So I like this, and again, this was emphasized in the video, the whole idea that the sun's about sending energy in all directions, okay? So here we see, and we're going to talk about, we have slides again to talk about how this energy that you see squiggling out from the sun, this is traveling at the speed of light, right? This right here, traveling at the speed of light. The energy to get out to the surface of the sun, now that takes a while. It takes like hundreds of thousands of years to ultimately work from the core out to the surface of the sun. So when we talk about stars next week, actually we're going to compare them to the sun. So the radius of the sun, you see the radius up there, about 109 times the radius of the Earth. The mass of the sun, you see how many of the Earth's masses it is. The video reinforced that when the solar nebula was forming our solar system, the sun got like 99% of the stuff, right? And like the 1% was, most of it was given to Jupiter, and then we kind of scrapped over the rest of it. But one of the things about stars is that their luminosities. And we're going to see that the sun in the kind of the broad spectrum or options of different stars is kind of a typical middle-of-the-road star. It's not really big and it's not really small. The sun isn't. The watts, you recognize the term watts? That's actually like when you get a light bulb out of the cabinet, you get a certain wattage. And that actually is saying how much energy is going from that light bulb, and so as we do that with stars too. But remember scientific notation, and we might run into this some more. Whenever you see something packed up like this, 3.8 times 10 raised to the 26th power, you definitely see that in astronomy. That means 3.8, and you move this decimal place over 26 places. So 1, 2, 3, 4, 5. 18, 19, 20, 21, 22, 23, 24, 25, 6. Okay, so each where I have a little circle there, you put a 0 there. Okay, and that's kind of what I mean by, or what they mean by 3.8 times 10 to the 26th. So just be careful of numbers packed up in scientific notation. What's the sun made of? Okay, not so surprising. It's mostly hydrogen. And then actually, did you catch this? That part of the theme of understanding stars and part of the theme of understanding our sun is it is converting hydrogen to helium. Hydrogen has 1 proton, helium has 2 protons in their nuclei. So basically it's taking hydrogen and making helium. I liked what the video said. It talked about how actually our whole solar system, the sun and the planets, were made from a star that blew up a long time ago. That was so cool. Okay. How fast does it rotate? I told you about a month. That's where this is. Okay. It has differential rotation, like the chick in the video said. Basically, it rotates faster and it's around its equator than it does at the poles. Surface temperature. This is actually, we ran into this temperature before when we looked at radiation curves, 5,800 Kelvin. That's the surface temperature. The core temperature is a lot hotter. One of the things we're going to see here in a minute is exactly what we saw in the film about the corona being really hot. Okay, the corona is much hotter than the surface. You're like, really? So you have the surface, you have the really hot core, the hot surface, 5,800 Kelvin. That's pretty darn hot. And then you have the corona, which is really, really hot. All right. Solar wind, right? That's what creates the comet tails. Okay, that's why they blow a certain direction. This term heliosphere, it's like this basically bubble in outer space that is created by the sun's solar wind. So we can kind of think of the sun's atmosphere as having 3 layers. In the video, I think. Okay. So the outer layer of the sun's atmosphere is the corona. Okay, and that is the hottest one. That's the hottest temperatures. Okay, and then inside the corona we have the chromosphere. Okay, so that's closer to the sun. And then under the chromosphere we have the photosphere. And the photosphere is kind of where the surface begins. So you see the temperature of the photosphere is about that 5,800 Kelvin. That's 6,000 Kelvin, 5,800 Kelvin. That's kind of what we call the surface. But it's kind of the surface, but it's also kind of like the lowest layer of the atmosphere. Then we have the interior of the sun. Of course, the core is the hottest, where, remember, only in the core can we have the hot temperatures and the high pressures for nuclear fusion to occur. And then outside of the core, we have these 2 zones that those cute little photons need to get past in order for them to successfully get to the surface of the sun. So remember they talked about the wandering walk or whatever? The wandering walk when the photon actually leaves the core and it's headed towards the surface of the sun. That actually is what we call the radiative zone. And that can take hundreds of thousands of years. Then after the radiative zone, we have the convective zone, or convection zone. We've talked about convection in here. It was basically where warm blobs of material rise, they cool down, and they sink, okay? And that's a little faster. So those two layers are shown over here, right here. So this would be the radiative zone, and this is the convection zone. You can kind of see these cute little convection cells. All right. So there are actually two types of nuclear reactions, and I want to kind of mention them. This one doesn't happen in stars. Fission actually is breaking apart. So this sort of nuclear reaction, if you've ever heard of using uranium in a nuclear reactor or uranium in a bomb, that would basically be taking a heavy atom like uranium that's unstable and breaking it apart. We talked about atomic structure, and those kind of creepy looking, they look like they're from Star Trek. Remember there's an episode in Star Trek where actually Spock kind of communicated with that kind of rock looking thing? That's what that looks like to me. So those are actually the nuclei of atoms. A large atom breaking into two smaller atoms. And this is, like I said, kind of uranium is a good guess for this. Now, here's one thing. I'm going to put, this is mass 1. I'll call this M1, and I'll call this M2 over here. If we were to compare the two masses, M2 would be less than M1. M2 is less than M1. So what's that mean? It means you lost some mass, and just basically in a nutshell, what you've done is E is equal to mc squared. What you've done is taken a certain amount of mass, okay, and converted it into energy. That's just what's happening there. Okay, but what's happening in our sun is actually this. Remember I said it's converting hydrogen into helium? Here you go. Here's your hydrogen nuclei. And here is, remember nuclei just means center of the atom. There's the center of the atoms, the hydrogen atoms. And He stands for helium. There's your helium atom. Now we're going to see it's a little more complicated than this. But again, if I put M1 and M2, here's what's going to happen. Actually, M2, that helium atom, is going to weigh less than the combined masses of those two hydrogen atoms. And where did it go? It created a lot of energy. And I know I have two hydrogen atoms forming one helium atom nuclei. Actually, we're going to see in next week where we're going to see stars actually can take helium, and actually our star will take helium too, and make carbon out of it. Okay, but anyway, that's what our sun's doing right now. So I think the video kind of talked about this basically soup of particles inside in the interior of the sun. Okay, so we're talking about kind of this nuclear fusion going on. I like this figure right here because this one right here is showing you what this does under, I'll say, low temperature, low pressures. Low temperatures, low pressures, basically you have this one combining with this one, like they're going to run into each other, but they don't stick. If you have high temperatures, I'll just put high T and P, high temperatures and high pressures, actually you're going to have a successful collision and they're going to stick and form, go from hydrogen to form helium. Now, doing so, they're going to lose some, it takes a lot of energy to make them stick like that. That's the high temperature and high pressures. And they're going to lose some mass, and that mass is what's converted to energy. Okay. So here's even more details. Notice I said you take two hydrogens and make one helium, but here I'm showing you you take 4 hydrogens and ultimately make one helium. The reason is a couple of those hydrogen a couple of those protons in the hydrogens turn into neutrons. Okay. But I usually don't test you over much of the details of nuclear fusion, but it is a little more complicated than I originally said. So, yeah. So how much energy is converted? A lot. Each second, 600 million tons of hydrogen is converted into just short of 600 million, or is converted into helium. So we'll take a closer look at, this is just showing you the nuclear fusion. The way you read this is, I guess it's over here. That pink box there in the previous slide is actually this pink box. And so notice what it is showing you 4 protons in, 4 protons. I'm going to go ahead next to the proton, I'm going to put the symbol H. Those protons are basically hydrogen centers. That's what goes in. And what goes out, okay, is 1 helium. And then you see the 2, 2, 2. Actually, the gamma rays are energy. Okay. When they talked about photons, that's actually gamma rays, energy / photons. And we're going to talk, kind of the last slide, we're going to talk about this little particle called a neutrino. I know neutrino kind of sounds like neutron, and we talked about neutrons. Neutrons are something you can sink your teeth into. A neutrino is like a little tiny particle that is created every time this happens, which this happens a lot in the sun. So one of the things scientists needed to do was to get a handle on the neutrinos. So bottom line, it is converting mass into energy according to E is equal to mc squared. All right. So remember I said that our sun is at gravitational equilibrium. Basically, the gravity would pull it inward. That's the green arrows. And the red arrows are the energy of the sun pushing the sun outward. Okay? So if it's in equilibrium, basically it's not shrinking and it's not getting larger. But it does to just a certain extent. So for instance, the way you read this is, up here at the top, it says, let's just say there is a slight drop in the temperature of the core. Okay, well, if there's a slight drop in the temperature of the core, okay, it is going to, you see how those green lines are a little bit bigger than the red lines? If it's a little bit cooler, then basically gravity is going to win out, so the thing's going to shrink down. So if you compare these two, you see it shrunk down a little bit. If it shrinks down, then guess what? If it shrinks down, then that means it's going to increase its temperature, and its fusion rate is going to increase. So guess what? It's going to heat up a little bit. Okay? So basically, what begins as cooling ends up as kind of restoring its heat again. And we could do the other also. So for instance, let's just say in this scenario it says that it gets a little bit warmer. Okay? If it gets a little bit warmer, then that means actually you kind of see this red winning out over the green. The red is the star putting out its energy, so it's expanding, it's swelling, and as it swells, basically that makes it cooler, okay, which slows down the fusion rate, okay. So it kind of has its own little thermostat, so it kind of combats, it wiggles a little bit in its size. One of the things I didn't realize, and I learned today at the Dr. Green's presentation, and this actually was one of Colin's questions, was Dr. Green said that Mars is going to get warmer, 7 degrees warmer, which is a lot, in the next, was it 1 million years? 1 billion with a B. In 1 billion years, Mars is going to get warmer. In 1 billion years, you know, the sun is still, you know, we say it's got 5 billion years worth of main sequence, you know, doing its normal thing. But what he explained was even though it's going to be kind of normal, our sun's going to be kind of normal, actually it keeps getting a little bit warmer, okay? So even though it's kind of in this equilibrium process, it is getting warmer. So this is actually the long walk. I can't remember what she called it, the meandering walk. You kind of see those little squiggles, those little pink squiggles. That actually is a photon working its way through the radiative zone. Remember, there's the radiative zone. There's the core, radiative zone, and convection zone. Okay? So that can take a long time. Long time. Okay. Now, what you're looking at here almost looks like a honeycomb. Like you could feel like a little bee could go in those little holes. Well, so this actually is the photosphere. This right here, the way you look at it, okay? This right here is like the top of the sun, okay? And then the core of the sun is down here, okay? And then we said that there's the radiative zone. And then we said there's the convection zone, okay? And so actually, as I think of it, This is kind of part of the convection zone, where basically you see material coming up, I didn't draw that very well, and then falling back down, okay? So these are hot areas right here, and kind of this circle, I'll draw it in blue, this circle right here are cooler regions. And this whole thing, let's see if I see it on here. Must be coming up. I'm going to go ahead and name it. It actually is, these circles are called granules. These circles are called granules. Granules, granules, final answer. So the granules are on the surface of the sun, and granules have nothing to do with solar activity. They do, but they don't. Granules are always there, whether the sun is active or whether the sun is inactive. And they're kind of cool. In the video they talked about, they're about the size of Texas, right? Granules. Okay, there we go. There's kind of a face-on look at granules. And they're animated. They actually kind of make you itch if you see a photo or a video of them. So I liked the video, and they said, like, remember they talked about the solar quakes and all that? Actually, that sort of kind of seismology is how we found out about the interior of the planets. And so we do a similar thing with the interior of the sun. Okay. Aside from that, this says actually physicists can understand what they know about nuclear fusion happening in the sun's core. Physicists also know, or scientists also know about heat transfer and all that, so they can kind of figure out what should be happening in the sun's interior just mathematically. This is the solar quakes, the solar vibrations. Okay. So it's a subtle thing, but that little picture there on the bottom that looks like a navel orange or something. Okay. So actually, there's kind of subtle regions of like little parts of the sun rising and falling. Neutrinos. Remember I told you a minute ago that we get 2 neutrinos for every successful, 4 hydrogens that go to form 1 helium. And we get 2 neutrinos. Well, the problem with neutrinos is that particular subatomic particle, that little piece of an atom, it basically goes right through matter. And so there's been a push to try to capture neutrinos in these awesome sort of, and I think I might have a picture. Yeah. That is a neutrino detector, okay? Probably that thing is buried beneath, like in some cave, right? Yeah, the bottom of a mine shaft, more than 2 kilometers underground. So what they do is they fill that with material that they're trying to basically have neutrinos run into and get a handle on them. I think they're better with neutrinos than they used to be. So that site called spaceweather.com, I'll go ahead and put it up here in case you missed it. Okay. So if you're coming out to the solar lab, so that's a deal where I'm going to set up the telescopes on the hill, and I'll have solar filters. Actually, I've got both the school's telescope and my telescope I can equip with a solar filter. We can look at the sun. Hopefully there'll be sunspots. But I will look there to see what sort of sunspots we have going on. In November, I think, like it's on a Thursday. Yeah. So this down here is actually showing you kind of the 11-year cycle, okay? Now, we say sunspots, but honestly, with sunspots come all those other things that you heard them talking about. Okay, so for instance, they talked about solar flares, okay? This isn't a solar flare. This is actually kind of a close-up of the sun. This is a sunspot group, kind of a cool sort of looking thing. Let's see, solar eruption. So over here, this one right here, okay, it said it led to a coronal mass ejection. So what you'll hear on the radio, or you'll hear them talk about CMEs, that is a coronal mass ejection. And that can be the granddaddy of them all. Basically, because of how fast it's going, how much momentum it has, material has left the sun's gravity and basically is being flung off somewhere. I like the way the video said it depends on if we are in the line of sight where we're screwed or not. So if that happens like on the back side of the sun from us, then we're fine. Okay? But if it's directly towards the earth, we have anywhere from like 12 to 24 hours to do something. And one of the things they said was actually you can power down your power grids, or don't have as much energy going through them. This one, the middle one, is showing you a solar flare. Okay, and then what we got down here. These are coronal holes, I guess I would say. I'll just even write that on there. Coronal holes. So the thing about the sun is, if you look on the internet for information about the sun, oh my gosh, they have so many observatories just looking at the sun for obvious reasons. We need to get a handle on what's going on with the sun to help protect our assets, quite basically. Not our asses, but our assets. What we do with the sun is look at it in different types of wavelengths. So the reason it has this like 11-year cycle, or that, and just the reason it has this ongoing kind of solar activity has to do with the crazy magnetic field lines of the sun. I thought the video did a great job. Instead of basically having a single North Pole, magnetic North Pole, and a single magnetic South Pole like the Earth, it's got, oh my gosh, like magnetic poles all over the place. So for instance, right here, it's just showing you just one particular, and these little black things right here would be sunspots. I don't know if you recognize that. Those are sunspots. So basically a pair of sunspots provide a location for a magnetic field to come out and go back in. And then the problem is you figure that their sun is actually rotating, okay? And that gives a spin. And they talked about basically a rubber band breaking. And so that's kind of why the rubber band breaks. Let's see, right here we've got, this is matter that's actually just kind of trapped in those magnetic field lines. They can give you what we call prominences and filaments. So this is showing you the differential rotation. Remember I said, and she said too, that actually around the equator it rotates faster. If you compare 1 and 2, you can actually kind of see these are flux lines being kind of rotated around. And here 3, I kind of liken it, if you've ever played Twister and you've gotten down the road maybe 5-10 minutes into Twister and basically everybody's arms and legs are all screwed up. That's what it reminds me of, basically magnetic field lines of the sun as it kind of gets down the road in its solar cycle. So, cool. So here are the questions that are due